Ma'am, could you repeat what you said about the pumping lemma, ma'am? Because my net had gone down. Actually, I'm really sorry, ma'am.
Okay, I'll repeat it some other time. Now, closure properties we will discuss on the basis of around 9 or 10 different operations. Okay, and the operations you can see on screen right now. And what is a closure property? I'm sure you have encountered closure as a closure property in discrete maths in the previous semester. Okay, when is a property, when is a particular operation said to be closed? It is closed when, if you apply that operation on the members of a set or a domain, etc., you get back another result which is again a member of that set. For example, we say that integers are closed with addition, with respect to addition, subtraction, multiplication, but not division. Okay, because if you multiply two integers, you'll get back another integer. But if you divide two integers, it is possible you will get a non-integer as an answer. Okay, so that is basically closed or closure property, and it is defined with respect to a set. Okay, a set of possible values, and also with respect to an operation which performs on that set. So the set we are discussing right now is regular sets or sets of regular languages. And the operations which we discuss, there will be several operations which we'll be discussing. Okay, so if on performing an operation on a regular set or a regular language, or maybe on two or more regular sets, if you get back a result which is again a regular set, then you say that that operation is closed for regular sets. Okay, so and while describing regular languages or regular sets, we can actually use any representation that we like. For example, we can represent using finite automata, which could be a DFA, NFA, epsilon NFA, whatever. It could be a regular expression. Okay, and subsequently, when we start discussing grammars, you'll see that we also have something called regular grammars, which represent regular sets. Okay, so regular languages can be represented in many ways. Excuse me. And we are now going to look at some operations which are closed for such regular sets. Okay, the first is union. Union operation means members of two regular sets, if you combine them together, what you get back is also a regular set. Now, actually, it is largely instinctive. Actually, we have often implemented this union operation in the form of this plus operand or operand. Okay, you have seen this in regular expressions. When you say R is a regular set expressed by a regular expression capital R, and same for S, then if you add this operation plus or in between the two, what you get back is another regular expression, and regular expressions, you know, they represent regular sets. So this is obvious. If union of two regular sets will also give you another regular set, which you can represent by this regular expression R plus S. Okay, and a similar idea you can also apply for concatenation. R dot S, sometimes we drop this dot. Okay, so R and S, if we write it one after the other, this is not the same as SR, please remember. Okay, so these are two different regular sets. So concatenation is also possible, and clean closure, that is R star, is a regular expression whose language is L star, as you know. So for concatenation and for clean closure, also, as well as for union, this definition comes, or this closure comes directly from the description of regular expressions. You know that. So these three operations are simple. So let's now look at complement. Okay, first of all, how do you define the complement operation on regular sets? Okay, how would you define complement? What is the complement of a regular set? It is defined with respect to a universal language. Okay, and what is that universal language? For a given alphabet, okay, for any given alphabet sigma, for example, your alphabet could be the binary digits 0, 1. just the set of binary digits 0, 1, then the universal set would be something like what would be the universal set?
Sigma star.
Sigma is not correct. What we will do is the pen not working. Anyway, the pen is seems to be. Just a minute, please. Let me try. Give me a moment. Let me just try getting this pen here. No, I'm sorry. I think it's not going to work today. I wish it had. So this is where we were. Okay, so the universal language now, the sigma, sigma, if it consists of 0 and 1, for example, then all the strings which are made up of 0, 1, you can actually represent by 0 plus 1 whole star.
Ma'am,
Okay.
are you presenting something, ma'am?
Can you not see my presentation?
No, ma'am.
Okay. Now can you see?
Yes, ma'am. Now it's visible, ma'am.
Okay. So what I'm saying is, if you if you take the universal set sigma star, and sigma, if you assume that it is 0 plus 1, then um, 0 plus 1 whole star is basically the universal set, which gives you every possible string that you can make up using 0 and 1. Okay, and since sigma star is a regular language, because you already have this regular expression for it, right? 0 plus 1 whole star. Okay, the complement of a regular language is also regular. So every string which does not belong to L but belongs in the universal set is part of the complement. So that is how we define the complement operation. All strings which do not belong to L but which are from the universal set. Okay. So how do we create the DFA for L complement? So suppose this is the DFA for L. Okay. What we'll do is we'll convert every final state into a non-final state and every non-final state into a final state. So this now is going to be the DFA for L complement. Now if you consider, what is L complement? L complement consists of all those strings which are not accepted by the original DFA. That means all those strings which are going to be ending up in some non-final state. Okay. That is assuming that the DFA is a complete DFA. What's a complete DFA? What is a complete DFA?
Ma'am, like any
Anybody?
DFA, ma'am, like any DFA that in which all the states go to the final accepting state, go to some final accepting state.
No, that is not a complete DFA. A complete DFA is one in which all outgoing transitions are defined for every state. That means from every state there will be one outgoing transition on every possible input symbol. Okay. Now if some of these will have a path to a final state, all the others might also go to what is called a dead state or a sync state. Okay. If this dead state or sync state is a non-final state in which all your unwanted transitions will end up. Okay. So it is somewhat like a sync. So if you have outgoing transitions for every input symbol from every state of the DFA, then the DFA is a complete DFA. If you have a complete DFA like that, then every string has a path in that DFA. Okay. And all those strings which do not end up in the final states will end up in the non-final states, one of which could be a dead state. Okay. And in such a case, if you interchange the final and the non-final states, remember the transitions, they are not changed, they are remaining exactly the same. Okay. Then now you are going to accept all those strings which previously you were rejecting. Okay. So this construction gives you a DFA. If not a DFA, it will give you an NFA certainly, which will accept all those strings which are rejected by the previous DFA. So this DFA now represents a DFA for the complement of L, which accepts the complement of L. Okay. So this is a construction. You can show that it accepts only those strings which are not accepted in L, and therefore this finite automata is a DFA for L complement. And because you have a finite automata which accepts all these strings and you can represent this by a finite automata, therefore L complement is also regular. Okay. So this is what is called a proof by construction. Okay. So this is your complement as it is defined, and then you have this construction which you can use to accept L complement. So this proves that complement is closed for regular sets. Okay. Now let's look at closure under the intersection operation. First of all, what is intersection? Intersection is defined for two. First of all, it is defined for two regular languages, L and M. Okay. And it consists of all those strings which are in both L and M. So you know what is an intersection of two sets, and these are regular sets after all. Now, a very easy way to prove it is by using De Morgan's law, as you can see. Okay. Because you can write intersection as L complement union M complement and the total complement of that. Okay. And here in this expression on the right hand side, you can see that we have used operations which we already know are closed. So L complement produces a regular set, M complement produces a regular set, union of these two also produces a regular set. Union, remember, it is closed. Okay. And then we are complementing the whole thing. That also produces another regular set. So obviously L intersection M is going to be closed for intersections. But there is a direct way, and we could construct a finite automata. Okay. Which often turns out to be very useful to be able to construct a finite automata. So we have two DFAs, A and B, whose languages are L and M respectively. So what we do is we construct what is called the product automaton of A and B. Okay. So let's see how the product automaton is constructed. So this is an example. We'll go back and look at the formal definition. So you have here two automatons. One is one on top with states A and B, and the second is the one here with states C and D. For the first one, the final state is B, and the second one, the final state is C. What kind of strings do you think are accepted by the FA on top? This DFA with A and B as states, what kind of strings does it accept? How would you describe it? You're not finding any description. So maybe strings which have at least one, okay, or if there is more one, then uh, I would say it is strings of zeros and ones ending in one. Would that be correct? What about the second one? So how would you describe this? So let's forget about the description here. So what is done in the product automaton is you take pairs of states. So states here are now represented by ordered pairs. Where have we used some construction like this before? Where have we used this before?
NFA to DFA conversion.
NFA to DFA, yes, that was subset of states, yes. But ordered pair we have used somewhere. Yes, in Murray and Mealy machine, do you remember? Converting a Mealy machine to a Murray machine. So we had used ordered pairs. Okay, here also we are representing each state by an ordered pair. Okay, the first component is a state from the first DFA, the second component is a state from the second DFA. Okay, and for example, on 0, from A on 0 you go to A, but from C on 0 you go to D. So from AC on 0 you will go to A and D. There's a transition to AD. Okay, so this product DFA, what it does is it basically simulates both the DFAs, that is the first and the second DFA, in parallel. It is like simulating in parallel. Okay, so for any input symbol, you can take any input symbol, say from state B on input 0 you go to A, and from state C on input 0 you go to D. So from BC on input 0 you go to AD. Can you see that how this product automation product automata is simulating this automaton and this automaton, both these two automatons sort of in parallel, and that is how the transitions are filled in for the product automaton. And how many states will the product automaton have? Here it is obvious, two from one and two from the other. But what is the formula? Suppose the first automaton has X number of states and the second automaton has Y number of states. Then how many states will you have in the product automaton? Have you heard of Cartesian product? Have you heard of the Cartesian product of sets?
Yes,
Why
ma'am.
is it that I am not getting any response today? Are you all worried about your tests or something?
Ma'am, actually, one section just had its test, so many people haven't even joined.
But so many people have already joined. Why you are not responding? What is a Cartesian product? Have you heard of Cartesian product of sets?
Yes, ma'am.
Okay. How many elements does a Cartesian product have? If one set has X number of elements, the sets here are the product are the states of the DFA, right? And the other set has Y number of states. Then how many states will there be in the product automated? X
X
into
into Y.
Y, obviously, right? So Cartesian product. So what we are taking in the product automaton is a Cartesian product. And this product automaton actually, it is used in many ways in many different constructions. We have already used some of them. We have seen that in NFA to DFA construction. That is not a product automaton, that is subset, but idea is the same. In Moore and Mealy machine, we actually have used a product automaton. And this is a very, very typical example of a product automaton because both the DFAs are being simulated in parallel. Okay, and the final state is the one whose first component is a final state of the first DFA and the second component is a final state of the second DFA. So please note that if any of these DFAs have more than one final state, you can have more than one final state in the product automaton also. This is a simple example where both given automatons have one final state each, and the product automaton therefore has just one final state, that is BC. Okay, B here from the one on top and C here from the one at the bottom. So this BC is now a final state, and this product automaton, it simulates both the first automaton and the second automaton in parallel. So for any given string, it is as if it will run it on the first automaton and also on the second automaton at the same time. And if it ends up in B for the first automaton and C for the second automaton, then it will end up in BC for this product automaton. And it will, if it ends up in B for the first automaton, it means it is accepted in L, and for C, it is accepted in M. And it will end up in BC only when it is accepted by both the input automatons. Okay, so only those strings which are accepted by both the automatons will be accepted by this product automaton. Okay, or the product DFA. Is this clear? Now let's see how this is formally defined. Let's go back. So closure under intersection. Remember, we are discussing the intersection operation, which consists of, that means intersection of two sets. You can see it consists of all those strings which are in both L and M. If you are looking at L intersection M. Okay, so let's construct a product automaton, and the final states of C, that is the product automaton, will be the pairs consisting of final states from both A and B. A and B are the given input automaton. Okay, so how do we formally define in terms of the 5 tuple? You know that all automaton are defined by a 5 tuple. Now, AL, okay, the first automaton is the DFA for L is given as QL, sigma. Note that both of them have the same input alphabet. So QL is the start state, final state, and then the transition function. Okay, and same for the second finite automata. And so we build the product automaton L intersection M such that the set of states is the Cartesian product of QL and QM. Okay, so this is the Cartesian product operation. Now input alphabet is the same. The state which is the ordered pair of QL and QM. Okay, this is the ordered pair. That will be the initial state of the product automaton. Final states also are taken. So remember, final states in DFA are actually sets. You can have more than one final state. Okay, so the Cartesian product of the final states of L and the final states of M, that means one component from FL, the other component from FM. Okay, so if you land here, you means you have landed in an accepting state in both the automatons for L and M. Okay, that will give the final states for the product automaton. And delta, of course, we have to define such that the first component is taken from the delta of L and the second component comes from the delta of M. Okay, where P is in QL and Q is in QM. So this construction ensures that when a string W will be accepted in this finite automata, that means it will land up in a final state if and only if it reaches an accepting state in both the input DFAs. Only when it reaches an accepting state in both the input DFAs will it be able to reach a final state in the product automaton. And which strings will reach a final state in both DFAs? Only those which are in the intersection of L and M of the two given regular sets. So by this construction, what we have now done is we have constructed a finite automata which accepts only those strings which are in the intersection of L and M. Therefore, it is possible to define L intersection M by a finite automata. Therefore, it is a regular set. Is this clear? This is how we proceed to define the closure of operations. So for intersection, we have given two different proofs. One is from the De Morgan's theorem, we have seen, and the other by creating a product automaton. This product automaton is very, very important. It's a very important construction which we'll be using again and again in various different ways. Please remember. Okay, now let's come to closure under difference. So difference is going to be the, what is the number of the operation? How many operations have we seen till now? We have seen union, concatenation, clean closure. Okay. Then we have seen complement, intersection, and difference is the sixth operation that we are discussing. Okay. So if L and M are regular languages, then so is L minus M. This is the theorem. This is the claim, you can say, which we are trying to prove. And what is L minus M, or the difference of L and M? Remember, it is L minus M is not the same as M minus L. Okay. So L minus M is defined as all those strings which are in L but not in M. Okay. So it is not the same as complement. Please remember, complement with respect to L only. You can say complement of M intersect L. Okay. So L minus M. So L minus M, here there is a complement missing. So complement of M intersection L. Now you can prove it by this, because remember, I'm missing that complement here. This M should be complemented. Now if M is complemented, it is producing a regular set. Then when you take an intersection of that with L, that is also producing a regular set, because we know that both complement and intersection are closed operations for regular sets. So L minus M is also regular, and it is also, so let A and B be two DFAs whose languages are L and M. Construct C, the product automaton of A and B. Okay. Now, how do you define the final states now? Make the final states of C, let the final states of C be the pairs where the A state is final. Why A state final? Because they have to be included in L, right? But the B state is not final because they must not exist in M. So all those strings which are accepted by L but rejected by M. So in the product automaton, what we now do, it is the same product automaton which we saw before. Okay, only we are now going to look at all those states which have the first component is B, because B is the accepting state of L, and the second component has to be D because D is not the accepting state of the second automaton of M. Okay, so BD now becomes the final state. The transitions, the states, etc., everything remains the same. Only the final state we have changed. By changing the final state, what we have got now is an automaton which accepts the language L minus M. Okay, this shows that it is possible to obtain an automaton which accepts the difference of two regular sets. And because it has an automaton, it is possible to represent this using an automaton. Therefore, L minus M is also a regular set, and difference is closed for regular sets. The difference operation is closed for regular sets. Okay. So this product automaton construction is a very, very important construction which we are going to be using here. Difference. In this particular example, the difference happens to be an empty language. Okay. Why is that? Can somebody tell me why that is, why it is an empty language here? What is the reason? Can you find any string which will be able to start from the start state and end in the final state BD? Yes or no?
No.
Is the final state reachable from the start state? All of you have studied some graph theory, I'm sure. Is the final state, is there a path from the final state to the from the start state to the final state?
No, ma'am.
No. Okay, there does not exist a path from the initial state to the final state. So it is not possible for any string to end up in the final state, as you can see. Okay, so in this particular case, okay, this is a particular example. In this particular case, the difference automaton also, the difference is an empty language, because automaton tells us very clearly that the only final state is unreachable from the start state, and therefore there is no string that will be accepted by this language, in this language. But you can see that by this means, this construction procedure, we can always create a finite automata which will accept only those strings which are part of the first automaton but not part of the second. Now what if you had to create a finite automata for m minus l? M minus L. See, I've changed the direction. This example shown on the screen is for L minus M, but I am talking about M minus L. In that case, which will be your final state?
AC.
AC. Yes, because it has to be the accepting state of M and the rejecting state of L. Okay. So accepting state of M is C and rejecting state of L is A. So AC is going to be the final state. So I think you are beginning to understand what I'm trying to say, and you have caught on to the concept of product automaton. And if this is the case, if AC is the final state, then what will be the language M minus L? Will it be empty? Just tell me that.
No, ma'am.
No. What are the possible strings? Can you think of any possible strings which will belong in M minus L?
Ma'am, one will belong, ma'am. Also,
One will not belong. If you start from the start state and you accept one, you will end up in BC, not in AC. You have to end up in AC, which is the accepting state.
ma'am, sorry, ma'am. One actually. It will be
Yes,
one.
1 1 is
Yes.
correct. 1 1 can come. 0 1 1 can come. Okay. 0 0 0 1 1 can come. So it appears to me all strings with ending in 1 will be able to come. Okay. And also the empty string. Empty string, if the initial state is also the accepting state, then the empty string belongs to the language. Okay, so M minus L is not an empty language, but L minus M happens to be an empty language. Okay. Um, so is this clear to all of you? This construction of a finite automata for the difference of two languages. Okay. So now let's look at reversal. Reversal, how do you define the reversal operation? The reversal of a given language or a given regular set is, see, this regular set is nothing but a collection of strings. If you take every string and reverse it, that means you read it in the opposite direction, starting from the last symbol and ending in the first symbol, then these reversed strings, the collection of these reversed strings is the reversed set LR. Okay, so reversal is defined with respect to the strings of L. When you reverse a regular language, you reverse every single string which belongs in that regular language. Okay, so if your L is consists of the strings 0, 0, 1, 1, 0, 0. Then LR consists of the strings. Now 0 you cannot further reverse it. Okay, so for strings of length 0 and 1, reversal does not have an effect. It's the same string. 0, 1 becomes 1, 0. 1, 0, 0 becomes 0, 0, 1. So this set now is LR. Okay, and how do we prove it? Give the proof for this. Again, we try to. Actually, we have two different proofs. We can prove by reversing the regular expression, and we can also prove by reversing the finite automata. So let's look at both of them. We'll first look at how a regular expression can be reversed. Then this is a very important trick which you must know, because you have been working with regular expressions. If you had to produce a reverse of a regular expression, then how will you set about it? Okay. Now, you remember, and I'm sure sir has insisted on this point very clearly, that a regular expression has a recursive definition. Okay, that means you define more complex regular expression in terms of simpler regular expressions. This recursive definition is very similar to your recursion which you have used in your programming. Okay, the programming construct of recursion. Recursion and recursive definitions, they have the same origin. And a recursive definition gives rise to recursion as an implementation. Okay. Now this definition of a regular expression is recursive in nature. The definition of a reversed regular expression is also recursive in nature. Okay. So for symbols which are epsilon, you remember the recursive definition of a regular expression, you have an empty set phi, or you could have epsilon, which is an empty string. Please remember, empty set and empty string are two different things. And then you have single symbols. All of these, when they are reversed, they remain the same. That is, E reversed, the expression for the reversed regular expression is also the same. Okay. So if you have a single symbol, that is strings of length 1 or strings of length 0, or even a language with no strings, then the reversed regular expression for that language is going to be exactly the same. Now, using this simplest induction stopping criteria, we will define larger regular expressions as f plus g. When you reverse a regular expression which has the form f plus g, where f and g are also smaller, simpler regular expressions, then you can write fr plus gr. Okay, so either you'll be using f or you'll be using g, and the reverse, to obtain the reversed string of the regular expression for the reverse string would be the reverse of f and the reverse of g with the operation. Similarly, the concatenation operation, again the reversal you can actually push it inside. Okay, so f and g reverse, but note that here the order is also reversed because we are looking at reversal. So G you first reverse, F also you reverse, then you look at GR dot FR. Okay. So that is going to be the expression for the reversed regular expression. And then if it is clean closure, F complement, then the reversed string will be produced by F reversed it's not complement, sorry, F star, then F reversed star. Okay, so clean closure also applies on the reversal. Inside, the reversal has to be pushed inside. So let's take an example to get this clear. So this is the recursive definition of the reversal operation on regular expressions. Okay, so how does this come? So let's take an example of 0 1 star plus 1 0 star. So which is the operation on the top? Which is the first operation to be applied? Remember the rules of precedence. Which operation will you apply first of all?
Ma'am, the star operation.
No, actually not. Now, I'm sure you have studied the rules of precedence with respect to arithmetic operations. Suppose you have an arithmetic expression with multiplication, addition, subtraction, etc. Which operation will you, and division also, which operation will you implement first of all? Which rule do you apply for precedence? I don't know why people are sleeping so much today. Have you not heard of the Bodmas rule? I'm sure you have heard it in primary school.
Yes. Yes, ma'am.
Yes, right? But Bodmas rule is nothing but the precedence of operations. Which operation should you attack first? Okay, you know that you have to first do multiplication and division, and then you must move on to addition and subtraction. Okay, similarly, in case of, and of course this precedence you can bypass by using brackets. If you have brackets, then you have to do what is inside the brackets first, right? In case of regular expressions, the highest precedence is given to which one? Clean closure, and then finally concatenation, and at the end you have union or plus. Okay, so plus comes at the end. You have to apply clean closure first, then concatenation, and then plus. Okay, so when we are reversing the strings again, we have to keep this in mind. So the expression for the reversal, first of all, reverse the entire expression. So this is a bit like, see here, the operation which is at the top of the parse tree is going to be your plus. Okay, so break into pluses. Here we are applying which rule? Let's go back to the previous slide. See, note this first rule here, f plus g. If it is reversed, it is fr plus gr. Okay, so fr plus gr. Okay, now this reversal we are going to push inside. So next is the concatenation operation between the two here, 0 dot 1 star, 1 dot 0 star. Okay, so when you are using reversal with concatenation, remember to exchange the order also. So 1 star reverse dot 0 reversed. 0 reversed is same as 0. Okay, plus here it is 0 star reversed dot 1 reversed. 1 reversed is again, since it's a single input symbol, it is going to remain the same. Okay, so 1 reversed remains the same, 0 reversed also remains the same. So what you are doing is you are applying reversal on this clean closure, and clean closure, remember, you will push the reversal inside. So 1 reversed, clean closure of that, 0 reversed, clean closure of that, and 1 reversed and 0 reversed are same as before. They remain unchanged. So what your final expression which you get is 1 star 0 plus 0 star 0. So what you can do to convince yourself is take this first expression, find some strings according to this first expression. Then second expression, find some strings, maybe strings of length 1, 2, 3 maximum. This much you can do because you know, since you have clean closure, these are going to be infinite sets. Okay, so infinite number of strings you cannot enumerate. Enumerate strings of length 1, strings of length 2, strings of length 3, and so on. Okay, and for this reversed expression, you enumerate the strings of length 1, 2, and 3, and see if you are getting the strings in reverse order. Okay, so this is going to give you the reversal of a regular expression which produces the reversed strings. So reversal as an operation is closed for regular languages. Okay, so to end today, let's just look at the construction for a finite automata which will accept the reversed set. Actually, it is quite simple. Since you have already done quite a few constructions, anybody, can you give a suggestion how we should set about doing this? Remember, we want the same strings. We do not want any extra string, only they should be accepted in the reverse order. So the last symbol which you had seen should now be the first symbol which you see. And the first symbol which you had seen should now be the last symbol which you see. Okay, So what do we do? Previously,
Change the
remember?
direction of the arrows.
Pardon?
Change the direction of the arrows. That means where we accept, now we will start like that.
Yes, very good. You have given exactly the correct answer. Thank you very much. We will reverse the direction of the arrows because we are moving in the opposite direction, certainly. Where we had ended before, there we will start now. And where we had started before, there we will end now. So that is very simple. Okay, it is exactly clear. So the new start state is going to be all the final states before. All the places where you had stopped before, that is where you will start now. Now start state is always a single start state. Okay, you cannot have multiple start states in a finite automata, even though you can have multiple final states. So what to get around this problem, what we will do is we will add a new start state, call it q dash 0, and we will add some epsilon transitions. Now you know that your epsilon transitions in the NFA, you can always get back a equivalent DFA, you can get back a regular expression, you can get back whatever you like. Okay, so it is not going to be creating problems. Then convert the old set of final states into non-final states. Reverse every arc. Okay, every arrow you reverse the direction. If it was pointing right before, now you make it pointing left. Okay, and what was previously the start state, now you make the final state. Okay, make the old start state the only new final state. So all those strings which were starting with Q0 before and ending in the final states will now start with those final states and end in Q0. So Q0 is the only accepting states. And remember, we have not introduced any new string because we have not introduced any new path. Okay, by adding a new start state, we have not introduced any new path. The same paths will be followed as before, only in the opposite direction, in the reverse direction. So all the strings, same strings as before, only in the reversed order we will be accepting now. So this is now the finite automata for, it is an epsilon automata, okay, epsilon NFA for L reversed. Is this construction clear to all of you? I think you are beginning to understand how we can work with finite automata to get different languages. Okay. Okay. Substitution onwards, we will continue in the next class, which is going to be next Tuesday. Okay. So we'll stop here today. And just for a quick recap, how many different operations have we looked at which are closed for regular sets? We have seen union, concatenation, clean closure, complement, difference. What else? Reversal. Am I missing out anything? Yes, I think 7 operations we have seen.
Ma'am, union and intersection.
Intersection, I think. Okay. So union, clean closure, concatenation, complement, intersection, difference, reversal. Yes. Okay. So these were the various operations we have seen. Particularly very important, you should understand how a product automaton is created. Okay, what is the product? It is basically simulating 2 different automatons at the same time. Okay, and by changing the final state, we can define the automaton for difference. Okay, L minus M, M minus L, or we can define the automaton for intersection, that is L intersection M, and so on. And in fact, we'll be using it later also for various different things. So this product automaton construction is an important construction. Reversal is important. Complement is important. Complement, remember, all the strings which were previously accepted will now be rejected. All the strings which were previously rejected will now be accepted. So we just interchange the set of final and non-final states. That's all. So I think we will stop here today. Your exams, I don't think I got around to modifying the notification on the Moodle platform, but I'll do it today. Your exams will be from 10 o'clock on Saturday, right? So on, I
Ma'am,
hope
it was
all of
11
you
o'clock.
have enrolled on Moodle. Anybody facing any problem with enrollment on Moodle? Yes,
No, ma'am.
Abhishek. Yes.
Ma'am, the exam was at 11 o'clock, na, ma'am?
11 o'clock.
Yes,
You
ma'am.
want it at 11 o'clock?
Yes, ma'am.
That's all right. That is all
Thank
right.
you.
That should not be difficult. So 11 o'clock on Saturday, you are going to have your exam. Is that okay with everybody? Anybody facing any difficulty with enrollment? All of you have enrolled, I hope. Now, since you have been using the Moodle platform for quite a while now, I'm sure you should not face any difficulties, but please make sure that you submit on time. Please make sure that you submit on time. The test will be mainly MCQ. But even if there is some non-MCQ question, please do not be hassled by it. Actually, we haven't finalized the exam set yet. Okay, but we hope that it will be MCQ. Whatever it is, it will be half an hour to 45 minutes. Note the time in advance. Note the time in advance and submit on time. Is that clear? All of you, make sure you give the test properly and wish you the best of luck.
Thank you, ma'am.
Thank you, all of you.
Thank you, ma'am.
If
Thank
anybody
you.
faces any difficulties with enrolling on the Moodle platform, inform Abhishek, and Abhishek, you can ring me up.
Yes, ma'am.
Okay. So you may leave today. Thank you so much.
Thank you, ma'am.
Thank you, ma'am.
Ma'am,
Yes,
ma'am, did you send any slides for the Mealy and Moore models, ma'am?
I think it's available on the Moodle page.
Yes, ma'am.
Okay. Moodle page, I think I have put up. I have not mailed it. If you want, I can mail it to you. If you don't get it from the Moodle platform,
Okay, ma'am.
please
Okay.
send me a mail. I'll send it to you.